Hello everyone. In this video, we will discuss about a problem from Munkres from exercise 2.2, which is problem 10.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Consider the unit interval I from 0 to 1 and give three different topologies to the Cartesian product of I and I. First is the product topology. Well, let us look into the basis set for this topology so that we are able to compare it. And first let us represent the topology to be TP and the basis to be curly B subscript P. So the basis is the collection of all open intervals where 0 is less than or equal to A is less than B, which is less than or equal to 1, and closed 0 and open A where again A is greater than 0, and open B to closed 1 where B is less than 1. So all intervals of this forms the basis for this topology. Okay, one can prove that this is indeed a valid basis for forming a topology from 0 to 1. So this is the basis for unit interval. If you were to find the basis for this topology TP, which is nothing but BP, it is the product of two open intervals like that. So like A comma B, A1 comma B1 cross A2 comma B2. Not only like that, you can also include 0 to A and B to 1. All those are included. For example, 0 to A1 cross B1 to 1, and 0 to A1 cross 0 to A2. That is also basis. Now coming to the next topology, which is the dictionary order topology. Let us consider dictionary order topology, which is TD, and let the basis of that be BD. So over here, the basis elements are just the open intervals and again the minimum number to some number and some number to the maximum number. But here the order that you put on the numbers will be dictionary order. On which number? On I cross I. What is dictionary order? You say that A comma B is less than C comma D if and only if A is less than C or A is equal to C and B is less than D. So basically, first you compare the first coordinate, this one, then if they are equal, go to the second coordinate in order to tell the ordering. Now once the ordering is understood, then dictionary order topology is simple. You just have the basis elements as all the open intervals from, let's say, from some M to N, where M and N are belonging to I cross I. And not only this, we know that the minimum element is 0, 0. So 0 cross 0 to some number M, or N to 1 cross 1. So all these form the basis element for this topology. Now coming to the third topology that they are mentioning, which is the topology that I cross I inherits as a subspace of R cross R. So in order to realize this, for the subspace of R cross R, you just consider the basis elements of R cross R. What are all the basis elements of R cross R? We know the usual topology that we put on R cross R is like A comma B to something like, let me write it in points. So suppose if you have x2 to x1, then that cross y1 to y2. This forms the basis of R cross R. This is the usual basis of R cross R. So if you go into the coordinate system, it will look like this. So if you have x1, and here x1 is less than x2 strictly, so x1 to x2 cross y1 to y2, which means this is your y1 and this is your y2. All these points will form, and this is open interval, so these boundaries are not included. Now this is the usual topology on R cross R, but here they are mentioning the dictionary order topology on R cross R. So this will not be your basis. Your basis will look like some m comma n again, where m is less than n in dictionary order topology. Right? So for example, if you have the point 2 comma 3 and you have the point 4 comma minus 1, then all the points in between them will form the basis. That is, this basis is represented as 2 comma 3 to 4 comma minus 1. All the points that goes till infinity. Now these are all the bases. Now we are only considering the subspace of R cross R, which is from 1 to 1. So in this subspace, consider the intersection of all the bases, and that will form the basis for this subspace, and that is called the topology that I cross I inherits as a subspace of R cross R. Okay, with this knowledge, let us define this as the basis with the subspace of dictionary order, BSD, and the topology to be TSD. Now let us compare these three topologies. For that, we would need to first consider the I cross I in R cross R. Because remember, there is also subspace of R cross R being considered here. So this point will be 0, 1, and this point will be 1, 0, and you will have to consider this segment and this segment, right? So this is your I cross I with the borders included. So borders are included. Let us remember that. The borders will always be included. Now first, the product topology, which was TP, and the next was dictionary order topology in I cross I, and the next was subspace topology with dictionary order topology on R cross R. So these are the three different topologies put onto I cross I with their corresponding basis element to be, the basis set to be BP, BD and BSD respectively. Now if you consider BP, we know that BP were of the form, if you go above and see, BP is of the form the cross of two open intervals like this. So you will have to consider some box like this, right? And all the elements inside, with it is like an open box. It is like an open box with all the elements inside to be the basis element. And pictorially speaking, your BD will be the dictionary order topology. So if you start from somewhere here, you will go till here, 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 and suppose if you end here, all these elements are the elements that are ordered between these two, right? Because their x coordinate is between them, because our x coordinate is our primary concern, right? Then we go and compare the y coordinate. Okay, then what will be your subspace topology? We know that in R, suppose if you start from here and put dictionary order on R, even the elements like this are open and elements like this are also open. So let us only consider this for now. So this is open in R. Now if you consider open in R cross R, now if you consider this its subspace with I cross I, since I cross I includes this border, so this will be, this green portion will be your basis element, because violet region was your basis element before the subspace. Now you have to intersect with the subspace, you will get the green portion. Now let us consider this topology, that is TP and TSD. Which one is finer or which one is coarser, or are they comparable? First let us try to answer that question. So in TP, we know that the basis elements are like a open box, right? Open rectangular box. So something like this. This is the usual thing. And now, if you consider any element inside this open box, we know that this dictionary order, what does this mean? Suppose if you have this point to be some, let's say u comma v, and this point to be some w comma z, then all the points, the x coordinate will be the same. So let us take it as u comma z. All the points in between them is an basis element in R cross R, and it is also basis element in the I cross I, because it is present entirely both in that subspace and as well as in R cross R. So it is open in the subspace topology. So what we can say is, for any point I can take, I can find the basis element in PSD, which is entirely present inside that rectangular open box, and it also contains this element, say x0, y0. So PSD is finer than TP, that is subspace topology is finer than product topology. Also you can consider the border elements, like including this. If you include this, we know in the subspace topology, if you want this element now to include, you can always find this basis element from TSD, which is present entirely in the open box, but remember this is not completely open because this line is closed. It is present in that violet box. So it is completely present in that violet box, and it also contains that green element of that violet box. And wherever if you go and stick onto it, and if you want to consider this element, then this will be your basis element from TSD. And if you consider this open box, then this will be your basis element from TSD, because we know that this is a basis element in R cross R. So its intersection will be closed in this boundary. So that will be always inside the violet box and containing that element. Now, let us try for the other way around. That is, we consider a point, and suppose you take this basis element of subspace topology. Okay, can you find a basis element from the product topology which is completely present inside this subspace topology? It is not possible, because we know that the product topology is always like a box, right? It is an open box, so it always looks like a box. So you cannot completely contained inside that line segment, because see, this line segment is one dimensional, but this is two dimensional. So always you could see that some points are outside of this line segment, which means it is not present completely inside the basis element of BSD. So TP is not finer than TSD. So it's not true the other way around. Now let us compare TD and TSD. TD and TSD is simpler because both of them look alike. And it also turns out that for any point that you take, any point that you consider, say x0, y0, and you draw the basis element from BD. Suppose say it looks like this. Then obviously this is also the basis, it is also present in the basis element of BSD, which means there exists a basis element in BSD containing x0, y0, and it is a subset of this basis element, because a set is a subset of itself, right? Again, if you you need not only consider basis element from BD like this, it might also look like this. But in any case, if you take whatever point, this is also a basis element in BSD, the same violet thing, because you just have to consider the corresponding basis element in R cross R, and it just extends till infinity, and you just find the intersection with this red box, which means this is also a basis element in BSD. So I can say that TSD is finer than TD. But let's go and look the other way around. You will be surprised for this. Suppose consider this basis element of BSD, the subspace topology, because we know that this is a open interval in R cross R by dictionary order. So you just take its intersection, right? Now, can you find a basis element from BD that contains this point? Let's say this point to be some x0, 1, or let us say 1/2, 1. Can you come up with the basis element from BD which is containing 1, 2, 1, 1 by 2, 1, and entirely contained in this basis element. It is impossible, because if you have to consider 1 by 2, 1 inside BD, we know that BD is of the form m, n, or 0 cross 0, m, or n, 1 cross 1. But we know that we have to take this m value to be less than 1 by 2, 1. Only then I can include 1 by 2, 1 inside this open interval, right? So if I take m to be less than that, then there will be some line. Let us say the m line is like this. This is say x equal to m line. Then there will be this line which is entirely present in that basis element that you consider, but not present in this violet line at all. So you will always arrive at a contradiction, right? If you choose a basis element of the form m, n from BD, because you can find a number x which is between, say n, which is between m and half. You can always find that such a real number, because we know that the rational numbers are dense, so you can always come up with the rational numbers between them. Now, this contradicts the fact that TD is finer than TSD, hence you cannot say. So this is not true indeed. Now let us go and compare the last comparison will be between TP and TD. Turns out that these two topologies are not comparable, because suppose if you consider this basis element of product topology. Suppose you consider this basis element of the product topology. And consider this point, say it to be 1 by 4, 0. Can you come up with, and let's say the maximum, this y line to be half. Can you come up with the basis element from BD which contains 1 by 4, 0, this point, green point, and entirely contained in this violet box? Right? Turns out that it is not possible. Why? Because if you have to include this, then m value must be less than 1 by 4. Because if m value is greater than or equal to 1 by 4, then 1 by 4, 0 does not belong to this. But we want it to be belonging to the basis element in BD. So 1 by 4 will not belong to this, which is a contradiction. So we want m to be less than 1 by 4. So if you take some value x is equal to m less than 1 by 4, again I can come up with this entire line which is between x equal to m and x equal to 1 by 4, which is at x equal to n, where this entire line is present in that basis element, but this entire line is not present in this violet box, which is obvious from the picture, right? Now let us also prove the other way, that is TP is not finer than TD. How shall we prove the other way around? For this, first let us consider a basis element from TD. So this one is going to be simple. Let us easily consider this basis element. Say we take 1 by 4, 1 by 2. Can you come up with the basis element from the product topology, which means rectangular boxes, right? The rectangular open box, or it can be closed in the borders, obviously. So that should contain the point 1 by 4, 1 by 2, and entirely contained in this green line segment. But it is not possible, because open boxes are always two-dimensional. So there will be some points that are outside this green line always, because these are boxes, right? It cannot be one dimensional. Hence, we cannot come up with a basis element completely contained inside this basis element of TD, the dictionary topology. Hence, TD is not finer than TP, which means they are not comparable. That's what we can say. So these two are not comparable. Thank you.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.